Good morning, everybody, to our next calculus class. As always, can I just get confirmation that everyone can see and hear me? And then we can get going. All right. Now, it's been a weekend, so let's just remember where we're at, what we did. The break at the end of the last class was a little unfortunate, but that's okay. Let us remember. So we are looking at the derivative as a function. So we have the original function. Let's say that's original function. Let's call it f of x, for example. Now that function has input, x values, that I feed into whatever the function does. I don't know the specifics. And then we have our output y value. Now y equals f of x, let's say. Now with the derivative, I have many different ways of finding it, but well, let's put it this way. I really only have one way to find it. I'll call it f prime. I can give it an input, x value, but let's maybe take another value. I think we call it c. Let me just be clear here, maybe a c. I feed it into essentially that limit definition. That is how we do it. That is the definition of the derivative. And of course, it's based on the function. The limit definition we have to memorize. There is technically only one way. And I would then get my output, which is some value, and graphically we can call this many things. Graphically, it's the slope of the tangent line. It's the instantaneous rate of change. Whoops, instantaneous rate of change. Some nice lag today again. Thank you, D2L. So regardless of how I want to interpret that, I give it an x value. I plug it into the limit definition, and I'll get, hopefully, a value. And I interpret that however I need to, whether I'm looking at a graph, whether I'm looking at rates of change, whatever that may be, it's all equivalent. But this limit definition is quite annoying to have to do repeatedly. So there are two levels that we want to get to. One level is to not do it for every single uh, x value, not a specific number here. Leave the C open, and then I can establish a rule, a general formula, if you will, for how to go from the x value input to the derivative value output. That's why we can see it as a function as well, input and output. So that's straightforward, but that doesn't really help me figure out how to get around this limit. So the next level is to look at simple functions, which we've started, and see, is there a pattern? Is there something we can notice when we do the limit definition, when we look at this input-output relationship that allows us to say, oh, well, for certain kinds of functions, I don't have to go through the limit, all that work. I can just establish rules sort of on a higher level that, yes, they do build on this limit definition, but they allow me to go around it and be more efficient. So what have we seen so far? Well, we went with our simplest functions. Uh, simplest case. Man, I cannot, what I write and what I see is not the same. So it's a little bit of a lag here. So my writing's a little sloppy. That's my excuse. I'm sticking with it. If I have my function, which let's just say in power of x, then we've established before that the derivative is going to be the power of x multiplied in front, that's a coefficient now, by x to the power 1 less. And we call that the power rule. Now this works, this is true for n. We started with x squared, x cubed, and so on. So it definitely worked for positive integers. Oh, this writing delay is horrible. I know it's D2L that's doing it. I'm just gonna, just give me a second. I want to see if anyone is in D2L because otherwise I'm closing this. It's nonsense. It's making my writing sloppy. It's making everything laggy. It's not efficient. Just trying to see who's in here. Yeah, I'm the only one. I'm going to stop it. Give me a second. Get that nonsense out of here. Okay, that should be better now. But now if my writing doesn't improve, oh, now I don't have an excuse anymore. Ooh, I didn't think this through. Anyway, then we also looked at, so for example, uh, x squared, x cubed, and so on. It all worked. We did a few of them with the limit definition. It was tedious. And then we noticed a pattern, and we just extended that pattern. Now, that doesn't qualify as a proof. You have to do it in general, but that using an x to the n is a little bit messy. I don't want to show that. It's a little outside of our focus, proving these things more formally. Then we looked at 1 over x, x to the negative 1, and we saw that it also works for n being a negative. Oh yeah, now the writing is way nicer on my end at least. Oh, so nice and smooth now. Also n negative integers. So that's quite a range. And if we did, for example, a couple here, if we say uh, let f be x to the 5, then the derivative is going to be 5x to the 4. So I just noticed that formula. If I look at a random negative power of x, let's say negative 7, then the derivative is going to be negative 7 goes in front, x to the 1 less, which becomes negative 8. So I always subtract 1 from the original power of x. Okay. So that's quite a bit. It's good progress with one rule. I don't want to call it a rule. One property that is coming from the limit definition. We can sidestep the limit definition completely, and that's my goal here. Let's now look at another example. Let's say I have a function here, and another basic function that I have is the square root function. I want to know what the derivative of this is. Well, it's technically not what I've seen before, so I have to go with the limit definition. That first time, whenever I see a function for the first time or a type of function, I kind of have to. Ooh, I don't know if we have space. Yeah, I'm just gonna go with it. So whether I call it C or X or whatever, some people get a little confused if I use an X here, still at this early stage. So I'll use another letter, but doesn't change the limit definition at all. It's whatever X value, whoops, whatever X value I am interested in. I just don't want to pick a specific number because then I don't see what the derivative relationship is with the function. I want to see this function aspect so that I can maybe see something that allows me to get around the limit definition and all its work. It is always there. That doesn't mean I always want to do it. So now let's see what we get here. Of course, we can't just plug in 0 for h. I'm going to have to see what the function is. Now it's the square root function. So inside the first one, I get a c plus h. Inside the next one, I get a c. Now, these kinds of things, yeah, they can be difficult. And this is a basic function. This is my simplest square root function. And even this, people might feel, I don't like this at all. Fair enough. But I want to show you, I want to at least see once how the limit definition has to be used to establish more efficient rules, at least in the beginning. So now what on earth do I do here? The form of this limit, if you look at it, and we should always look at the form of the limit, of course, is 0 over 0. Because at the top I'll get a root c minus root c, which is 0, over h being 0. Yeah, 0 over 0, unfortunately. So that means look at the function, look at what I have, and see if I can simplify that. But looking at it, it's not a rational function. I don't factor it. I don't do things in the same way. It's a different kind of function. There's a little trick that I can do that is something that you don't have to come up with. You just have to see it once and sort of learn from it. I'm going to multiply this whole thing by 1. And because it's by 1, I haven't changed a thing. But now I'm going to see 1 as 1 over 1. Still haven't done anything because I'm just multiplying by 1. Now I'm going to write this fraction in this 1 in a very, very fancy way. I'm going to write it as the root of c plus h plus root c over itself. C plus h plus root c. Why? Well, we'll see in a second that it's going to work. And because I have the numerator and the denominator the same, I've only multiplied by 1 and I haven't changed anything, so I can still say equal here. Now I'm just carrying the limit with me here until I can simplify this in some clever way. So now I have at the top the root of c plus h minus root of c times root of c plus h plus root of c over the bottom. I have an h, and then I have the root of c plus h plus root of c. Okay, but the top is more important right now. The top is what's important because I remember that if I have an a minus b times an a plus b, that simplifies to a squared minus b squared. It's the difference of two squares. And that's exactly what I have here. The same thing's in the bracket except one's a minus and one's a plus. So that means I have the first one squared and the second one squared. And my bottom stays the same. Nothing is happening there for now. So now I'm just going to make a new page while you think about what happens at the top there. The square and the square root are sort of defined to cancel each other out. It's kind of what the square root does. So I'm just going to continue up here. I'm looking for my derivative, right? So I have, limit. Let's just write the limit there. We're not ready to really use that part. It just goes with us everywhere. So this first one is going to be c plus h, because square root and square they cancel each other, c plus h. The next one is just a c, and then I still have the messy bottom portion, unfortunately. I'm not too worried about that right now. I'm just carrying it with me to hopefully see something eventually. So now I have this c and this c canceling each other. So what do I have now? I have only an h at the top, and then I still have the same bottom, c plus h. Oh, a stupid truck in the background here. Hopefully it doesn't bother anyone too much. Now the h's can cancel, and I'm making good progress. And I have 1 over c plus h square root c square root. Now what is the form of this limit? It doesn't really matter. What matters is not dividing by 0 anymore. There's no zeros anywhere in numerator, denominator, nothing. So this is well defined, so to speak. It's defined at h equal to 0. The limit is just going to be what I get when I plug in 0 for h. And then I get 1 over 2 root c, because I have 2 of the square root of c. Now I know that was a little long, messy, something I should see though. Agree to disagree, but you should see it once. This trick, whenever I have the root issue in a limit, often this trick is by multiplying by a fancy 1, so to speak, can help me simplify things to a point where I can eventually just evaluate the limit easily. But regardless, so if whether you perfectly followed that, whether you need to look at it again, doesn't matter. The point here is if my function is the square root function, then the derivative function, whether I use a c, whether I use an x, doesn't matter, it's an x value, just temporary placeholder, is 1 over 2 root x. But notice that the square root of x is x to the 1/2. So I can see the function, this basic square root function, I can see as power of x. And so far, all the powers of x that I've looked at seemed to fit the power rule. But I haven't looked at fractions until now. The roots are fraction powers of x. Can I simplify this guy to write it as a power of x? Well, it's definitely 1/2 derivative here, right? Because the 2 is in the denominator. And then I have an x to the 1/2 at the bottom, which becomes x to the negative 1/2 when I move it to the top. Now, what would the power rule suggest? The power rule says take the power of x, take the power of x, move it to the front. Okay, the power of x was 1/2. It is at the front now. And then the new power of x is 1 less. Well, 1/2, what it was originally, minus 1 is negative 1/2. So the power rule works in the sense that following the power rule gets me to the derivative function as well. And in fact, that's true for all the fractions. In fact, I'm just going to put it over here. Power rule is true for all real numbers, real values of n. Yes, integers, negative, positive, fractions, anything at all. The power rule works. So it is quite powerful. Get it? Power rule, power of x, powerful? No? Okay. In that it covers a lot more functions than we originally might have thought. Okay. Power rule. Any power of x. If it's x to the power of something, the power rule will help me. So it's actually a very, very important and I don't say versatile property. Versatile, sure, let's go with versatile. It's a very versatile property in that it handles a lot of functions, but still basic, right? It still has to be only x to the power of something. I don't have a lot of flexibility, but in terms of what that power, that exponent can be, lots of flexibility. Okay, so let's just go on a side note here. Let's have a side note where I just want to explain the different ways we can write the derivative. One is the prime notation, where if we have my original function and it has a name, f of x, then the derivative function is called f prime of x. And that's very handy. If I have a function name already assigned to something specific, I often want to name the derivative in an appropriate way corresponding to that function. So that is definitely sort of a standard way and one that we'll see more often than anything else. So let's just give this a heading here. Derivative notation. Ooh, my writing is not good today. Ooh, terrible. Let's try that again. Notation. How do I refer to the derivative? One way, if I have a function name, I can use the prime notation. Great. We also have what I'll call, I don't know if it's official. It's not official. I'll call it little d notation. Little d notation. Because the derivative is the slope of, let me just call the function here. Usually we call the function y in this case, but it can be anything, function name. Usually, well, not usually, the derivative refers to the slope of the tangent line. And slope is change in y over change in x, or for short, delta y over delta x. Now, that's the slope of a secant line, so I can't use this exactly. They change the deltas to little d's, and they write dy, function name, over dx. Now, mathematically, these little guys called differentials have some more properties, but for now, really, it's just a name of the derivative. I could have called the function f and then say df dx. It doesn't matter. It's just a different name for the same thing. And then I will lastly have big D notation, where I have my function. Let's call it y. And then I'm going to name the derivative. Of course, we're doing the exact same thing. It's just sometimes certain names are a little bit more convenient to illustrate properties. I'm going to use a big D for derivative. And I'm going to say what the variable is at the bottom. And then I'm going to put the function or its details in square brackets. All of these things are all the same. Some, we'll see in time, are just more convenient than others. Right now, we haven't had a need for switching up the notation, but in my opinion, for certain properties that are coming up, it's a little bit more clear if I use a different notation. Sometimes. People can disagree. Personal preference is all this is, really. Okay. So let's make a page, a new page, where we are just going to list all the properties that we know so far. And there's only one. Okay, so let's call this derivative properties. And I'm going to use my big D notation because I want to get used to it. And it doesn't get enough attention. It should get more attention. If I have my variable x, and in my function that I'm looking at is x to the power of n for any n, well, that's not 0. I should probably say that. Derivatives n, not 0. Of course, if I have something to the power of 0, it doesn't really make sense to look at it as a function because it's just 1. So that is an exception, I suppose. The power rule says n goes in front, new power of x, 1 less. Power rule. So see, the big D simply means derivative of whatever is in the square brackets. That's my function. I could name the function f of x, or I could have the detail of what the function actually is. And then I have a little subscript next to the d to indicate the variable in question. Later on, that's going to help me to do something. Right now, it's just something that needs to go with it. And for most of our situations, it'll be an x. But it's whatever variable is in the question. Sometimes we mix it up with a t or something like that. Okay. So I'm going to keep this page nice and clean and do some motivations for where these other properties are going to come from on another page. Because as nice as x to the power of something is, we have at the very least transformations of those functions. So at the very least, we know that we can transform. So what about transformations of these basic functions? We can transform x to the power of, or x squared, x to the power of whatever, and make other functions. We might want to know what the derivative of those functions are as well. So for example, I want to maybe know what about if my function is 3x squared? What then? What do I do about that? Right, that's not the power rule. So the question is, what is the derivative? And the answer is not use the power rule. Because I want to make it clear, people are very sort of relaxed about these rules. The power rule says one thing. It says if I am looking at x to the power of something, there is nothing else in these square brackets. It has to be just x to the power of something. Then this is what the derivative is. This is how the slope of the tangent line behaves, rate of change, whatever you want to refer to. Yes, this function that I have here is very similar. It's certainly related. It's a transformation of x squared. It's not x squared. The power rule is not immediately applicable. However, it's also not far off. If I look at x squared and I graph a little parabola here, whee, there it is, a little flat, but oh, that is not. I'm going to go with this one because it's not going to get any better. And I transform it to 3x squared. What is happening to the graph? It's happening. Everything gets stretched a little bit, right? Now we are taking an informal approach to this. I totally agree. The basic idea really is that let's suppose we look at a line point there, a slope of that tangent line there. If I look at the new position of the point, the slope is going to be steeper. And in fact, it's going to be steeper by a factor exactly what the coefficient of the x squared is. Now, of course, that's not a proof, but we can say it like this. We can sort of argue it graphically for a simple function that we understand and say the derivative of 3x squared. It turns out if you do it precisely, you measure the slope and have specific examples, it is going to be the same as 3 times the derivative of the basic before the transformation function. So that means that if I generalize to the derivative of any function, sorry, any number multiplied by a function, could be just x squared, could be something more difficult, doesn't matter. It's going to be the same as the number times the derivative of the simpler function. And this is where the big D notation is handy. It can write symbolically the property that I can say in words, of course. If I have a number times something in x, could be just x squared, could actually be anything, then I can simplify the situation. And how I simplify it is that number that the function was multiplied by can be in front and multiplied with the derivative of just that function. Because what this does is a stretching of whatever I had, and the slope stretches as well by the same factor. Of course, this is not a proof in any way. Let's just see a proof of this fairly simple one to give you an idea of we're not making this up. We're not looking at a specific example and argue that, oh, the slope looks 3 times steeper than the other slope. Therefore, in general, it's always going to be. No, 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 no. If you prove these things, for the most part, it has to be by way of the limit definition. So let us pick a function. Let me make this function maybe something else. For consistency, people might get confused if I mix up my names. We can call it anything. Let's call it g of x. Doesn't matter. Let's say we have a function, and that function is some number times a simpler function. Think 3x squared. 3 times x squared. Okay. To find the derivative, the derivative only has one definition. Whatever form I'm looking at, it's the limit definition. Now I'm going to use an x again because I think we are ready for it. It's the limit definition in the only form, in the only form I am going to bother to remember. There are variations of this. They're not benefiting me in this case. I just want to give you a taste. You don't have to remember how to prove it or anything. I just want to emphasize where these things come from. They have to be officially proven through the limit definition. Whether we might see all of those proofs or not, that doesn't mean they don't exist. Now, the function f is a number a times some other function g. So f of x plus h is a times g of x plus h. F of x is a times g of x over h. Then we can factor out an a and write g of x plus h minus g of x over h. Then, because it's all multiplication, I can put the a in front multiplied by this fraction. Now here, you just have to believe me, we've avoided talking about limits more than we need to. We focused on what the mathematical language is behind the limit concept as a behavior of something. But there are properties and things that allow me to work with limits in calculations that I avoided. It's in most books, but I don't really find them very useful. You go through a lot of effort to memorize limit properties that you almost never use. But there are limit properties that say that if I have two things multiplied together and one of those things do not depend on the limit variable in question, then it can be taken out of the limit and multiplied after the fact. If you don't uh, understand where this comes from, it's because we never did. We never did it. We never emphasized it because we were never going to use it. But in these proofs, these limit properties uh, do come up. And if you want to understand the proofs, then you would need to understand those limit properties. But it's sort of a sidetrack that I don't really want to go down. I just want to see this once. So now I can see here that what's left in the limit is exactly the limit definition for the derivative of g. Derivative of g. So let me zoom out. If I have a function that's a number times something else in x, the derivative is that same number times the derivative of the x portion. Or in big D notation, up here, it's the same thing. Different notations for the same thing. So that applies when I have a function that is broken up into pieces, some constant, some number times a function, another function. So I will call this the constant times a function property. It doesn't have a very nice name. I just made it up. I have a constant times a function. I'll call it the constant times a function property. I know it's not very original. I'm sorry. Simply says that if I have a number in front of the x stuff, that number can stay in front and I can focus on the derivative of the x stuff, what I call the essence of the function. The essence of the function is determined uh, by where the x's occur, where the variable occurs, not the constant in front. Okay. So now in combination, these two can be used to determine the derivative of, for example, 3x squared. I need more space. But it's very important to understand that each property allows me to do only what that property says. And by realizing that, I am going to avoid a ton of mistakes. So let's suppose I want to find the derivative of 3x squared. Still not a complicated function. It's one transformation of the basic function we know. The first property I'm going to use is the constant times a function property. And I'll write it short here. Oops. Constant times a function property. Then that property allowed me to isolate the power of x. And for that derivative, I can use the power rule. The power rule was not ready initially because the power rule said, where is it? Only what it said. I'm only ready if you give me a power of x and nothing else. Well, I wasn't quite ready for that. But I have another property that can isolate that power of x, and then I'm ready for the power rule. I can then simplify this to 6x. Okay. Very important in the beginning, right beside your line, each property that you're using. And we're going to add more to it as we go. So right now we have these two properties. But you can then say, well, what about another transformation? Like if I have the, oh, no, let's not do it this way. If I have the function x squared plus 3. What about that? So for that, I need more properties because I need to isolate the pieces that I see in this function. The derivative properties that I have so far don't handle when things are added together. So I kind of need more properties. Now, those properties, I will say again, need to be proved by the limit definition. It'll look very similar to this, but of course not exactly the same. Know that those limit proofs are out there. We're just not going to look at each one of them because it's not the focus. Next property is the sum. I'm going to leave a space here. The sum property that says if I can see my function as two functions added together, then I can look at the derivative of each of those terms and add them up after the fact. That also works for a minus, and that's why it's called the sum difference property. If I have a plus, if I have a minus, I can isolate the terms, look at those derivatives individually, and then put them together. And that's exactly what I would want to do. If I look at something like this, now I can say, well, the derivative is going to be the derivative of the first term plus the derivative of the second term. I want to be able to look at them in pieces, and when I actually find the derivative, it's of something small and simple, and then I'll reconstruct the derivative of the original function. So this one's going to be okay, right? This is going to be x squared. So power rule says 2 times x to the power of 1. I'm going to put them together by the sum property. So this is going to be the sum property. But I don't know how to handle a constant function. That's not in my list. A power of x, a number times a function, constant times a function, two functions added or subtracted. I need a constant property. And we're going to call it the constant property. These names aren't super creative, I'm sorry. It's going to tell me what to do if I just have the function equal to a number. I need a constant property for this one. And of course, for this one, I have the power rule done. Now let's think about the derivative of 3. What does that mean? It means I have y equal to 3, and I'm looking for the slope. Derivative is the slope. Well, what does this function look like? It's a horizontal straight line at 3. What is the slope of a horizontally straight line? I know, you all fell asleep. I'm sorry. It's 0. Yes, it is. So it's not hard to convince yourself that the derivative of a constant should be 0. And it is. It is 0. Because that's a horizontal straight line. Constant function, 0 slope. We've already seen that. All right. So a lot of things happen here, though. All the properties come together to give me the answer. First, I had multiple terms. The sum property was first. Then I could look at them in isolation. Well, the first term was just the power of x. Power rule handles that. The next term was a constant. I now have a constant property that handles that, and I can simplify it and be done. So all of these guys come together, and it's very important that I know what I'm using and when I'm using it, when I'm not ready to use it, what I need to do first, the sequence of properties that are being applied. That will help me to avoid mistakes. Let's look at a couple of examples since we have some time. But what's left to do for tomorrow is to just do problems, as many as we can, to really get used to how to safely look at these things. I have my list. I have my list of properties. It's not super long. I have 4 of them. We'll add some more later. They're never going to be super long. It's a question of which one do I use when, which one do I not use, and so on. For example, I could look at 5.2 number, sure, let's go with 3. Now, in the beginning, we are going to make a big deal about how we use the properties because it's important. But as we get used to it, we'll slowly write a little bit less and a little bit less. But in the beginning, I strongly encourage you to write out everything. There may be a question in a test that requires me to do this much detail. So I want to be ready. But I will say we won't do every one of these. By the end of tomorrow, you'll see we'll streamline this as we get used to it. Sorry, I'm speaking and trying to copy this down. That's never going to go well. Now, I know this might be a thing. I'm running out of space. I'm just going to put it underneath. So the question is, now we don't have a lot of time here. We're going to do this in a lot of detail where I want your opinion and your feedback as we go. Right now we have 2 minutes. So I'll run you through how this is going to look, and this is what we'll do tomorrow over and over and over until we're super comfortable with it, because this is at the heart of what we're doing in this course. The derivative is the core concept behind everything. So first of all, I have to isolate the terms. The first term is 5x cubed. Now I want to do one property at a time to really emphasize and check that I understand what is used and when. So I isolate the terms, and what I've done is the sum. What I've used is the sum difference property, right? Sometimes a sum, sometimes a difference. That's okay. Now I look at each one and see, oh, there's a number in front of the essence of the function. For the first one, I can put the 5 in front, and that is the constant times a function property. Now I'll do the same property for the second term, putting the 12 in front and leaving just the x squared. Whoops. But I won't do that one yet. I'll do one at a time. Okay. Maybe next. Let's just finish these terms. Let's just finish the first ones. Now I have the power of x isolated. The 5 is there, 3x squared by the power rule. The 12 is there for the middle term, x squared's derivative, 2 goes in front, x to the power 1 less. We don't write the 1. Power rule again. And I'm doing one property at a time. I still have to figure out this last one. So now I can simplify if I want to. I could leave it like this. It really doesn't matter. I could write 15x squared. I could write 24x. I can leave them. Doesn't matter to me. Lastly, the derivative of 15 is 0 by the constant property. And then I can simplify that further. Not that I mind that the 0 is there. And we're done. Now, of course, this is our first example. I just wanted to squeeze one in. All we're going to do tomorrow is practice the basic properties. I'm pretty sure that's what our schedule allows. But it is up to you to actually do that one line at a time. Which property comes first? Every semester, I write a function or derivative question like this, for example, and I ask, okay, which property should we use first? It is 50% of the people say the wrong property, which means that when it comes down to it and they have to do it, they don't really know what they're doing. And that's when mistakes are going to happen. And that is what we're trying to avoid. So I have to be very aware of what each property is saying and what it's not saying, when it's applicable, when it's not applicable. Yes, we get used to them very quickly. That's our goal tomorrow. But that cannot replace the detail of what's truly happening when I pull it all apart and explain it one step at a time. Eventually, as we get used to it tomorrow, we'll start doing multiple things in the same line. But don't do that in the beginning if you're not ready. All right. Any questions at this stage before we pause it for more practice tomorrow? All right. Until then.